Hello everyone, my name is Matthew Joslin and I'm from the University of Texas at Dallas. Today it's my pleasure to present to you our work titled Double Face, Leveraging User Intelligence to Characterize and Recognize AI-synthesized Faces. This work is with Xian Wang and my advisor Shuang. Recently we've witnessed a surge in real-world incidents involving AI-generated images. For example, AI-generated images have been used in a suspected spy's LinkedIn profile, a high school student's political candidate, and groups of Facebook profiles spreading polarizing content. However, existing analysis and detection approaches have limitations. Existing detection approaches use off-the-shelf classifiers, which can be susceptible to picking the superficial features. Another line of work is based on the heuristics of individual researchers, but these are limited to individual perceptions and assumptions. In this work, we develop a novel approach that uses crowdsourcing intelligence to characterize and defend against AI-synthesized images. We focus on human face synthesis as this poses high practical threats and social engineering attacks, and research into neuropsychology has shown that the human visual system is sensitive to facial information. To study this topic, we designed our study around 4 research questions. We took 2 sets of 100 AI-synthesized faces from StyleGAN 2 and StyleGAN 3, and also included 100 faces from a real dataset for comparison. We then asked 185 users on the mTurk platform to annotate these images. Specifically, we asked these users to provide a fidelity rating to help answer our first research question of whether AI-synthesized face images contain artifacts users commonly perceive. We also asked users to annotate artifact locations to answer our second research question of where in AI-synthesized face images these artifacts are located. In addition, we asked participants to describe the artifacts that they had annotated to answer our third research question of what patterns these AI-generated images exhibit. Finally, we applied attention learning to answer our final question of how we can use the user's perceptions to improve the detection of AI-synthesized faces. To collect the user annotations, we developed an annotation interface for the mTurk platform, which consists of the following 3 steps. Step 1 requests participants to draw boxes on top of the image to locate suspicious regions that they perceive. When boxes are drawn, the boxes are assigned indexes for reference in step 2. And we dynamically add text fields on the web page and request participants to input text to describe the pattern of the annotated region. Finally, step 3 asks the users to select the rating choices to indicate how fake the image appears using a predefined 5-level Likert scale. To answer the first research question of whether AI-synthesized images contain artifacts users can perceive, we analyze the fidelity ratings given by users and the average number of boxes annotated by users per image. In this figure, we can see the distribution of the average fidelity rating. The x-axis is the average fidelity rating computed by converting the descriptive 5-level Likert scale shown to the users to integers from -2 to 2. We use an average score of 0, corresponding to a level of not sure, to separate perceptions between fake and real categories. On average, over multiple users, 89% of real images are rated towards real, and 65% of synthesized images are rated towards fake. On average, we can see that users indeed recognize the difference between AI-synthesized and real face images. This figure gives the distribution of the average number of boxes per image drawn by participants. The x-axis represents the average number of boxes over participants for an image, while the y-axis shows the cumulative percentage of the images. We observe that 52% of real images have less than 1 annotation on average, while 6% of synthesized images have less than 1 annotation. The results show that participants carefully examine the images and annotate more frequently in synthesized images than in the control group. Here, we can see some examples of user annotations on AI-synthesized face images. We had 15 users draw bounding boxes for each image to locate suspicious regions. We use heat color to indicate the number of annotations aggregated for a position, where red shows high annotation levels. To identify commonly annotated regions, we develop an algorithm based on a union-find strategy to extract connected components from the bounding boxes drawn by multiple users. In the interest of time, the algorithm details are described in the paper. Here, you can see some examples of regions extracted by our region extraction algorithm on the AI-synthesized face images that we just saw. As you can see, the algorithm extracts compact, suspicious regions which were commonly annotated by users. Based on the extracted regions, we answer the research question of where these regions are most likely to occur in AI-synthesized face images by aggregating the set of location noun descriptors that each participant gave to identify where these regions are at. Our objective for this analysis is to identify specific areas where synthesis artifacts are present in AI-generated faces. We group them into 15 frequently occurring categories, including 10 facial on the left and 5 non-facial categories on the right. This figure presents conditional probabilities for these different location categories shown on the x-axis. The y-axis indicates the conditional probabilities of these categories. Overall, our analysis shows that AI-synthesized images exhibit statistically significant higher conditional probabilities than the control group of real images. We see that facial regions exhibit varying degrees of probabilities for AI artifacts. Areas like ear and hair are more likely to show defects discerned by users. These areas distant from the central face have high levels of distinguishable artifacts. We can also see that non-facial objects, including hat, earring, and clothes, show consistently high likelihoods of artifacts as compared to the control group of real images. With the conditional probabilities calculated over all non-facial categories, the non-facial regions in synthesized images overall have 6.6 times higher likelihood of being annotated as suspicious. The observations show that non-facial regions frequently contain artifacts in AI-synthesized images. Now that we've seen where the artifacts are more likely to occur, we'd like to determine what types of patterns these artifact regions exhibit. To do this, we can correlate regions by the location that we've determined earlier and the pattern adjective terms that participants gave to find which patterns are most frequent. Next, we examine what types of patterns these artifact regions exhibit. We calculated the conditional probabilities of description words from the pattern prompt based on the location tokens that we extracted earlier. We also checked the statistical significance of the difference between the real and fake correlations. In each grid, the bottom left triangle represents the correlation for synthesized images, while the top right triangle compares it with the real images. We find that users perceive different patterns for similar locations in synthesized versus real images. In this figure, blurry in the first column is strongly correlated with regions like ear and mouth. The pattern unnatural skin in the second column also correlates highly with the facial regions in synthesized images. This figure focuses on the correlation between non-facial regions and their descriptive patterns. Like the facial regions, the most prevalent synthesis pattern identified is blurry, being prominently associated with non-facial regions. Furthermore, we detected specific non-facial patterns like unknown object, which was correlated with clothing, and mismatched, which is associated with earring. These findings indicate that the synthesis patterns in non-facial regions frequently do not align with recognizable objects. We further investigate how user perceptions can be used to facilitate detecting AI-generated face images. We use the aggregate user-annotated regions to provide extra guidance to a detection model using an attention loss. Our method uses an attention mask, M, extracted using our algorithm, which highlights these high consensus areas on synthesized images. We adopt an attention learning framework developed by Li to generate a model attention mask A, which pinpoints discriminative regions identified by the model. To align the model's focus more closely with human insights, we introduce a mean square error loss between A and M, as detailed in this equation. We first take the pointwise loss or squared difference between the model's attention and the mask we have generated. We then sum these terms pixel-wise over indices I and j. Finally, we normalize this term by the size of the mask between 0 and 1. By minimizing this loss, the attention map A is refined to closely mirror the user annotation mask M, which ensures that the network focuses on the regions flagged by human annotators. This table shows our detection F-score results. The training method column denotes what type of training was used for the detection approach. The same methods as training columns use the train test split across StyleGAN2 and StyleGAN3 images. Other StyleGAN-related model columns were testing images generated by other models related to StyleGAN. Other model columns were testing images generated by other synthesis models. The last column shows the arithmetic average across all testing datasets for each detection. Each testing scenario consists of 1,000 fake images compared with a set of 1,000 real images. As you can see, our attention learning approach with human annotation achieves high accuracy compared with the other approaches. We also performed evasion experiments, which are detailed in the paper. To summarize this work, we've shown how to characterize artifacts that users commonly perceive in AI-synthesized face images. We've also identified the prevalent patterns and locations of artifacts in AI-synthesized images. And finally, we've shown how to incorporate our attention learning method with user annotations to improve detection of AI-synthesized faces. Thank you so much for coming to our talk. I'm happy to take any questions now.